A 5 kilogram ball is suspended by two strings, one horizontally attached to a wall and one attached to the ceiling at a 30-degree angle, as shown in this figure. So part A, draw and label the forces that act on the ball. And instead of drawing a separate dot for the free body diagram, we're going to draw the forces directly on the figure. So we can start with the usual, the gravitational force, going straight down, so labeled as Fg. And because the ball is not on the surface, there's no normal force and there's no frictional force, but there are two strings connected to it, and each string has a tension. So we can draw a tension along the direction of the string, labeled Ft, and also slanted on the string attached to the ceiling, labeled as Ft. But the thing to be careful of is that these two tensions are not the same. They're two separate strings, so you cannot just leave them as Ft and Ft. You have to differentiate between them. So one might be like Ft1 and Ft2, or in this case, I'm going to call it Fth for the force of tension in the horizontal spring, and Fts for the force of tension in the slanted spring. Part B, calculate the tension in the slanted string. Before we move on from this problem, we have to first take this free body diagram and we have to break it into components. So I'm going to draw a separate dot, and I'm going to keep the few forces that are already on the XY axis on there just as they are. So we have a gravitational force going straight down, and we have the horizontal tension force, Fth, going to the left. But now the Fts, we've got to break that into both a horizontal and a vertical component. So notice the Fts is pointing both up and to the right. So we're going to have two separate arrows, one going up and one going to the right. And using trig, we can see that if we go back to the original free body diagram and draw a dotted line in the x-axis, that this angle right here, which I'm going to call theta, is exactly the same as the 30-degree angle right there, because this angle and this angle are alternate interior angles, if you remember that from geometry class. So because this angle right here is 30 degrees, or theta, I can say that the horizontal component is going to be Fts cosine of theta, which I'll put right here, Fts cosine of theta, and the vertical component is Fts sine theta. Now that everything is broken into components, we can solve part B, calculating the tension in the slanted string. Since the ball is not moving, that means this is going to be a Newton's first law problem, because all the forces are balanced. The up equals down, left equals right. So if you look at the diagram, let's see if it's better to do the horizontal or the vertical direction first. In the horizontal direction, we have a force to the left, which is Fth, and a force to the right, which is Fts cosine of theta. Now, we don't know Fth or Fts. They're both unknowns. So in the horizontal direction, we have two unknown variables. But if you look in the vertical direction, we have Fts sine of theta going up, and we have Fg going down. We don't know what Fts is. That's still one of the unknowns. But we do know what Fg is, because Fg is just the gravitational force, m times g, and we know mass, given in the problem, is 5 kilograms, and we know g is 10 newtons per kilogram. So because we only have one unknown in the vertical direction, we're going to start with that direction. So we'll say, identified as a Newton's first law problem, net force in the y direction equals 0. And by saying that, that means we can establish that the upward forces equal the downward forces. So we can then write the upward force, Fts sine of theta, is equal to the downward force, Fg, which if you want, you can just go ahead and write that in as m times g. And then rearranging this equation to get Fts by itself, we can just write Fts, divide both sides by sine of theta, so you get Fts is equal to mg divided by the sine of theta, which is 5 for mass times 10 for gravitational strength divided by sine of 30. That's going to be equal to 50 divided by sine of 30, which is 1/2, and 50 divided by 1/2 is 100 newtons. So the slanted string has 100 newtons of tension in it. Now let's look at part C. Calculate the tension in the horizontal spring. Now going back to looking at the horizontal parts of the resolved free body diagram, there are two unknowns, except one of these unknowns, the FTS, we've just solved for. So really we just have FTH left. So for part C, we can write down Newton's first law in the x direction. Net force in the x direction equals 0, which means we can set left equals right. So I'll say FTH is equal to the rightward forces, which are FTS cosine of theta. And now since we're solving for FTH, all we have to do is just plug the numbers in. FTS we just solved for as 100 times the cosine of 30. So that's going to be 100 times the cosine of 30, which is the square root of 3 over 2. And if you simplify that down, 100 over 2 gives you 50 times the square root of 3 newtons. So that's the exact answer to this problem, which could show up in a multiple choice question, but they could also give you a multiple choice answer as a decimal approximation. So you could just put 50 times the square root of 3 in your calculator, and you would get an answer of 86.6 newtons for the approximate answer. Okay, so the 5 kilogram ball is now replaced by a 10 kilogram ball. Does the increased mass cause a larger tension in the slanted string, the horizontal string, or both? Now, people might be tempted to say that it only causes a larger tension in the vertical string because that's the one that has, or the slanted string, because that has a vertical component to it. So an increased gravitational force, because the mass is bigger, would just cause an increase in the FTS, the slanted string, because it has a vertical component. But what you have to look at is this. Let's look at everything in terms of the equations. If you go to this equation, the first one you derived, an increase in the mass right there would lead to an increase in the slanted string. And then if you look at the other equation, well, this one doesn't have mass in it, so you might be tempted to say that an increase in mass does not affect the FTH. But what it does have in it is an FTS, and we just said the increase in the mass will increase the FTS, the tension in the slanted string. So because that is part of the equation, that means this would increase, which would then also cause the FTH to increase. So the answer for this one is that both strings would have a larger tension when you have an increased mass. And for your justification, you can just put the mass increases, so that means that the tension in the slanted string would increase according to this equation, and because the tension in the slanted string increases, that means the tension in the horizontal string increases according to this equation. With the 10 kilogram ball still in place, the slanted string is now replaced by a longer string, which is attached to the ceiling at a new location so that the other string remains horizontal. So what that's saying is that this string right here is just going to become longer, so it's going to go from here, maybe like out to here. So what that would change in this problem is that you could imagine if you had a longer string, it would just make this angle a little bit smaller. So we're decreasing the value of theta. So in part E, does the tension in the slanted string increase, decrease, or remain the same? So let's go back to the equation for the slanted string, which is this one right here. In this equation, if you decrease the value of theta by making the string longer, you would also decrease the value of sine of theta. And when the denominator decreases, that means that the whole entire value would increase. So a longer string means a lower value for theta, which means a lower value for the sine of theta, which ultimately means a larger value for the FTS. So FTS will increase. And in part F, does the tension in the horizontal string increase, decrease, or remain the same? So in part F, we know that we just said that the FTS increases. So because the FTS has increased, just like the answer in part D, an increase in the slanted tension would lead to an increase in the horizontal tension. So in part E and F, both tensions will increase when the string is replaced by a longer string, leading to a smaller angle.